What are polymers? Polymers are like Legos or building blocks that can be assembled into larger, more complex structures. The way they are put together can give different structures and properties. More unique and complex assemblies can give you things like this. You've probably seen numbers and triangles on various items in your households, but what do they mean? Each one describes a different polymer with different properties. Number 1 stands for PETE and stands for polyethylene terephthalate and is found in your water bottles. Number 2 stands for HDPE and it stands for high density polyethylene and is typically found in soap or detergent bottles. Number 3 is for V or vinyl, which can be found in polyvinyl chlorate or PVC pipes. Number 4 is LDPE and is low density polyethylene. These can be found in your typical grocery bags. Number 5 is PP, which stands for polypropylene and is typical in Tupperware or storage containers. Number 6 is PS, which stands for polystyrene and is in your styrofoam cups or to-go containers. And number 7 is for other, which can be things such as water jugs, gas containers, CDs or DVDs, and bulletproof vests. Polymers can be characterized by their low densities, ease of molding, and their low moduli. The modulus of a material is a tendency of it to deform along its axis due to opposing forces and can be expressed as a ratio of stress and strain. Most importantly, polymers show a unique characteristic of behaving both elastically and viscously, a term we call viscoelasticity. The elastic behavior of a material is its tendency to resist deformation and return to its original shape once the force is removed. Viscous behavior is a measure of a material's resistance to shear stress and dissipates energy added to the material rather than conserving it. No other type of material shows this, making polymers highly desired building blocks. Mechanical properties of polymers are dictated by their glass transition temperature. The glass transition temperature is the temperature at which the structural behavior of a polymer changes, as shown here. Starting here in the rubbery region, the polymer is more flexible and returned to its original shape after deformation. It is believed that we see this behavior because the polymer chains have a higher energy and therefore more free volume to be moving around. As we cool the material, we begin to see changes in the polymer's physical properties. At a certain temperature, we see a departure from the state that the material wants to be in, and we see the material begin to harden. After passing through the glass transition region, the volume is less dependent on the temperature and the polymer chains become more packed together and lower in energy. As this happens, they begin to take on a more solid-like structure, and this is called the glassy region. We can see these changes in mechanical properties when looking at a stick of gum. A stick of gum behaves very similarly to a polymer at varying temperatures. When we are above the glass transition temperature, the polymers will show a high flexibility, and you can see this in the gum as it becomes softer and begins to stretch and bend as force is applied. The polymer can also be pulled apart easier as the forces holding the chains together become weaker with an increasing temperature. As we cool the polymer, we pass through the glass transition temperature into the glassy region, or the region where the polymer becomes more stiff. The chains here are packed in closer and do not have the ability to move as readily. The polymer will break into larger pieces with more well-defined edges, rather than being pulled apart and easily deformed. All polymers show this phenomenon, and this phase transformation determines the usefulness of polymers in different applications. In today's world, we are seeing many of our technologies move to a smaller size scale. Airplanes and other modes of transportation are designing parts composed of polymer nanocomposites for their low densities and high strength. Integrated circuits are manufactured with nanoscale conducting polymers to increase the functioning speed for our electronics. Despite the growing need for nanopolymers, further advancement has been hindered by our lack of understanding at the nanoscale. As we approach polymer films with thickness around 100 nanometers, we start to see some interesting changes. The glass transition temperature that is responsible for so many structural characteristics is subject to change, and as a consequence, the polymers can start to behave differently to temperature swings. This is called TG confinement effects. Depressions in TG can lead to structural changes like those seen in the stick of gum example. This can cause problems at the nanoscale in electronics, such as your cell phone. Nanoconfined polymers typically see a decrease in the glass transition temperature. If this happens, stiff structures and circuit boards can alter as they transition from glass to rubbery and cause problems in electronics. In this example, you can see the rigid nanopolymer structure begin to relax and develop elastic properties as a result of the decreased glass transition temperature. In electronics, these structures have very specific electric currents running through them which allow your cell phone or small device to operate. If these structures become elastic, as shown, the touching can cause short circuits to fry your phone. These effects are observed but not very well understood, making them very complex areas of research. The two major factors that are attributed to dictate the magnitude of these effects are surface effects and intrinsic size effects. Intrinsic size effects are those that arise only from the polymer approaching the nanoscale. This can be seen solely by reducing the dimensions of the polymer to below 100 to 200 nanometers in thickness. When reducing the thickness of polymer films, you might expect to see flimsy or weak behavior. However, when you start approaching 200 nanometers or less in thickness, these polymers tend to lose their elasticity and become stiffer, and that's about 500 times thinner than a piece of paper. These polymers are showing what is called the rubbery stiffening index, which is another property that is subject to change at the nanoscale, in addition to the glass transition temperature. The rubbery stiffening index is a measure of how stiff or strong a polymer is. Some polymers are seen to have an increased stiffening as the film thickness is decreased. Take a long stick, for example. By applying forces at either end, you can observe bending or warping in the stick, which is analogous to a thicker polymer with less constrained chains. When you shorten the length of the stick, it becomes stiffer and less susceptible to bending and warping effect, which is like a polymer showing an increased stiffness as you decrease the film size. Surface effects are those that arise from the interactions between the polymer and the surface it is in contact with. This surface can be a flat substrate, a nanoporous material, or even a liquid. What is important about these surface effects on the nanoscale for polymers is that these effects can overshadow those of the intrinsic size effects. A good example is a polymer's mobility dependence on surface interactions. When a polymer is in contact with the substrate, the surface energy pulls the molecular chains, constraining them and reducing their mobility. The mobility of the polymer molecules is an important factor determining the glass transition temperature. Surface interactions with the polymer greatly influence the mobility of the chains. The mobility of a polymer molecule is an important factor in determining the glass transition temperature. Surface interactions with the polymer greatly influence the mobility of the chains. Jello confined in a dish provides a great visual example of how surface interactions from the substrate affect the mobility of the polymer. Notice that the Jello is more mobile the further away it is from the edges of the dish. The further away a polymer surface is from a substrate, the less confined the molecular chains are. Typically, the more mobile chains of a polymer, the lower the glass transition temperature. No matter which area on the jello the force is applied, the center is still the most mobile. Now, the jello is not in contact with the outer surfaces of the dish. The bottom, however, is still in contact and adhered to the dish. When the jello is not in contact with the outer surface of the dish, it becomes more mobile throughout the material. We take this a step further by removing the jello completely from the dish, showing its increased mobility when the surface interactions are completely removed. The loss of surface interactions drastically increases the mobility of the polymer. A higher mobility will correspond to a lower glass transition temperature. This can change the properties of the polymer and must be taken into account when designing materials. Polymers already have a very defined industry in our everyday lives, as water bottles, storage containers, or building materials. But the more we begin to learn about these difficult molecules that are increasingly difficult to study, the more uses we find. The more we can understand about what drives materials' varying properties, whether it be intrinsic size or surface effects, for example, the more applications we can find and hopefully improve technology, transportation, and overall everyday life. Thanks for watching.